Hi, hope everyone can hear me. So this talk is going to be about almost like a classic Web 2 problem almost. It's purely a problem of how do I execute blockchain transactions efficiently with some safety properties that we're looking for. So just to sort of recap, the standard model here that we work with is, a block proposer proposing a bunch of transactions, right, in a block. The block is prepared and it's sent off to each validator. And each validator is trying to execute this block in order to reach an agreeable state of the outcome of executing the code in each of those transactions within that block. Now, the state of the art, at least in Ethereum, is to execute this sequentially. So, if you get a block of transactions, if the block follows a preset order, so to speak, you execute it sequentially, and all is well. So now you get this determinism, right? So, you can sort of append that block to the previous block and, everyone sort of reaching this mutually consistent state, which is great. So you can imagine like a simple coin transfer, a complex smart contract, ERC20 contract, any of these, right? And you can sort of talk about the same in the context of sort of a Move virtual machine or, a Solana virtual machine or, any sort of Ethereum-based clients. But in many ways, right, it's sort of sacrilegious to sort of imagine having like, a 24-core, 48-core AMD EPYC machine, right? And you're sort of executing all of these transactions sequentially. And this is a huge performance bottleneck in many ways. So what, one of the main things that, a lot of the blockchain ecosystems are striving for is to maximally parallelize this execution of transactions within a block. And the goal is to sort of maximize CPU utilization and minimize the memory footprint of this execution. Okay, sounds simple enough, right? So you have all of these like hardware threads and you spawn all of them and you let them run in parallel and you aggregate the output and you get it. But that doesn't quite work because now you might end up having conflicts, right? At the end of the day, this is a distributed system. And a distributed system means that there are causal relationships that you have to respect. In terms of transaction dependency. So our goal is to resolve these transaction conflicts in a block and maximize, the execution throughput. But more importantly, unlike sort of a classic parallel execution problem for those of you who are familiar with it in the Web 2 world, in the Web 3 world, we have to follow this preset order because the model is that the block proposer gives you the set of blocks to execute. And additionally, the order in which those blocks have to be executed because each of the validators are trying to execute that block and they have to reach an output that is consistent with each other at the end of the day. And so you are expected to respect this preset order. So given that this preset order has to be respected, and we are still trying to sort of get the maximum amount of parallelism, how do we do this? So this is sort of a very classic problem. And this problem is something that manifests itself in classic database theory, classic parallel execution. But in the Web3 world, we are constrained by this so-called ordering curse, where you have to respect this preset order. This is almost a problem which has nothing to do with Byzantine or malicious failures. This is a classic problem, classic fault-tolerant distributed computing problem in the benign world. I'll talk a little bit about the implications for it in terms of other models, but in many ways, this is a very classic, fault-tolerant distributed computing problem. The problem is that, you have to respect this happens before relation, right? So this is a distributed system. There is no time. There is only causality. So you have to respect that, that intricate relationships in terms of who reads state from whom and the order in which that is executed. Because otherwise you run into this classic scenario, right? Like where you think that there is a certain amount of state in an account, but it's probably not because you executed the transactions in a different order. It's the simple case of sort of, two people concurrently withdrawing money from a bank account, right? So you and your significant other try to withdraw money from the same bank account. Both of you think you have $100. Both of you withdraw $100, but only one of those transactions can succeed. So, we are trying to respect this order. So if you sort of visualize this, this is, if you depict this as a sequence of transactions, I'll just sort of give you a mental model for what can go wrong, what qualifies as unsafe here. So here you have two transactions, just, T1 and T2. In this case, transaction T1 is trying to read some account X1. Let's imagine the initial value of this account is 0. And then transaction T2 comes and it's trying to read in the state of an account X2. Let's imagine that its value is 0. And then it's trying to write, to an account X1, and then transaction T1 is trying to write to an account X2. So you have transaction T1, which is reading from an account, which transaction T2 is writing to, and transaction T1, which is writing to an account, which transaction T2 is reading from, right? So they have this, cyclic dependency on each other. Now, the problem is that, if T2 commits before T1, the preset order is violated, because in this case, it read a value that it ideally should have read the value that T1 wrote. So if it missed that, then you violate this preset order. The other option is to re-execute. And when you re-execute, in this case, you can sort of see that, okay, the resulting serialization is T2, T1, and even in this case, the preset order gets violated. So what you really have to do is have transaction T2 wait for transaction T1. So this is what we call the ordering curse. So even though I have two hardware threads and I'm trying to exploit my concurrency, I really can't do anything here because I'm forcing transaction T2 to wait for transaction T1. And this is the preset curse that, the preset ordering curse that all blockchain, parallel execution algorithms have to deal with. And one of the solutions that people talk about in terms of, building this in a sort of highly concurrent way is to leverage what is known as transactional memory, which is sort of, which is sort of transform the sequential code to a piece of concurrent code, which sort of resolves data races and conflicts and gives you a provably correct execution. It's sort of a one-stop solution to transforming any piece of sequential code to a piece of concurrent code. And the idea is that this gives you determinism and safety, and all validators get the same post state even when the transactions are executed in parallel. Now, there are different models for this, and one of the goals of my talk is to just give you an insight into sort of the taxonomization of this world, and sort of leave it to further discussions later. Now, there are, many ways in which you could do this. You could sort of maintain multiple versions of every account, or you could just imagine having a single version of every account. So this is an example of a single version where, just because two transactions are writing to the same account, you could maintain both those states, both those values in your persistent state, or you could just forget as soon as you write to one and write in place and so on. So if you imagine sort of the classic single version where you try to minimize your memory footprint and try to maintain exactly one value associated with every account, there are severe restrictions that you have to wait for. So now you'll have to sort of wait for transaction T1 in this case, right? So to complete and transaction T2 comes through. The other option is to leverage, sort of keep all possible versions of everything that you're trying to write to. And here, there are some benefits, but in most cases, there aren't, actually significant benefits, because in this example, as you see, I don't really get any advantage by keeping both versions. In this case, both versions here being both 0 and 1. So if I make both those versions available for transactions to read, then I can pick and choose which one I want to return from in order to get the most amount of parallelism. And here, multi-versioning is not useful, but you could imagine a scenario where, I have these two transactions where transaction T1 is just reading, to X1 and X2, and I allow both to run concurrently. And even though transaction T1, which is reading X2, it has to return the initial value, which is 0. So even though it's running concurrently and I have transaction T2 writing to 1, if I maintain both values of the accounts, 0 and 1, then I do get some benefits out of this. Now, there are some advantages of maintaining all of this extra state and extra memory footprint, but it turns out that you'll really have to maintain all n versions of the account in order for some sort of safety property to hold. So the idea here is that if you go sequential, everything is hunky-dory, everything is fine. If you go fully parallel, you get the maximum possible execution, the maximum possible speed up, but the execution could be unsafe. And you're somewhere in the middle where you have to respect this preset order, which is bounded concurrency, and yet you're sort of faced with some of these lower bounds where you'll have to maintain, all n versions in order to get, the best possible progress. So your trade-off is it's sort of a space-time trade-off where the amount of memory footprint that you have to maintain against the maximum amount of speed up that you could possibly get. The other problem is that you'll also end up having to, limit the kind of concurrency that you can get, because you get these like longest conflict chains. You could imagine a transaction with n blocks where, Tj is dependent on Ti, for every j and I, right? So if you have like, T1, T2, T3, you have T2, which is dependent on T1, T3, which is dependent on T2, and so on. And so you get these like longest conflict chains, which are very rare based on our studies. But this is, again, something that limits limits the sort of performance that you can get. So there are, broadly speaking, this is sort of my taxonomization of this world. There are these two ways of thinking about it. One is sort of what I like to call the read-write aware execution, where you have some information a priori about the nature of conflicts. So the Solana virtual machine is one such example. And the other world is this read-write oblivious model, where you're completely oblivious to the nature of dependencies and to the nature of conflicts, and you're sort of running optimistically and trying to hope that everything will be fine. And if something goes bad, which you detect algorithmically, then you would roll back your state and then try to fix any problem that might have happened because you read an inconsistent state. And this taxonomization is I'm giving this more sort of to build a mental model of sort of, the parallel execution landscape, but it manifests itself in so many different ways. But broadly speaking, I think it's useful to think of this as one setting where, there is, you do not have any information about the nature of conflicts in a block, and you're trying to execute this in parallel. And the other setting, which has fully detailed information about the nature of conflicts in the block, and then you're trying to get the maximum possible parallelism. As you can imagine, the setting which is oblivious is probably going to limit throughput, because you'll have to, do algorithmic work in order to detect your dependencies. The setting in which you have the dependency information a priori, you could intuitively get significantly more parallelism. How do you get those dependencies? Well, that's an open question, and there are several sort of algorithmic models at play here. But for those of you who are familiar with sort of the smart contract ecosystem, Solana is an example of a virtual machine which is sitting in the read-write aware model, whereas the Aptos Move virtual machine is sort of more in the read-write oblivious model. And one interesting question that we decided to ask was, okay, is there a world that is between the two? Is there a world where, we could sort of build algorithmically some of these access specifications, these conflict dependencies, and leverage that information in a best effort manner in order to bridge the gap between the performance of both the worlds? And that is sort of my insight into this talk, so to speak. We built this block transactional executor, which is somewhere between the read-write aware model and the read-write oblivious model, which algorithmically derives the dependencies of transactions in a block using static analyzer techniques, and thus tries to eliminate the need for costly re-executions and still try to get the best possible performance. So the idea here is to come up with sort of a just right Goldilocks approach, right? So where you're not spending all of this effort building the perfect, sound and complete specification, but you're rather sort of trying to do just enough in order to get as much performance as possible. I'll just give a little bit of insight into the nature of the implementation. This is primarily an implementation built for EVM, but we also have implementations of it for Move. The main takeaway is that, yes, this is feasible. You can sort of build a provably correct, and when I say provably correct through formal method tools, that this is like a safe execution. And you do see a non-trivial speed up over sequential. So, 3 to 7x performance improvement on most workloads. and this is sort of a synthetic workload, but you also see significant performances even in historical workloads. Now, historical workloads are typically smaller, right? Not significantly a large number of transactions in a block, and you probably don't get like huge benefits when the transaction size when the block size is really small. But there are interesting things to learn from it. And broadly speaking, this approach sort of also allows you to build a more adaptive parallel execution algorithm where you don't see like big differences between different workloads. So you get stability across sort of wide-ranging DeFi workloads, which is critical also to sort of having a good homogeneous performance across your validators in the distributed setting. So I'll just conclude this talk by saying that there are a huge number of open questions which are like classic Web 2 questions, but which are very different in the Web 3 world. Parallel execution also has significant implications for MEV mitigation because there are several ideas that you could imagine in terms of how you characterize dependencies and use this to prepare your block at the mempool level itself so that you get a conflict-free execution when it goes to validators. You could also transpose this problem in the Byzantine setting where you allow as part of consensus to decide the nature of the block that needs to be executed. There are also significant questions in terms of how we would, leverage parallel execution in a way that's also not significantly I/O intensive because this talks to the database a lot and we want to minimize I/O performance. So tons of open questions. Every virtual machine is very different. There are like several Ethereum clients which are proposing several variants of this read-write oblivious or read-write aware models. Similarly, with the Move virtual machine, Solana virtual machine, again, has its own proposal for it. All of which I think raises some very interesting questions because both CPU-intensive tasks, which is execution, and I/O-intensive tasks, which is fetching state for execution from persistent memory, are huge performance bottlenecks right now. And this is something that we are constantly trying to sort of understand and evolve. And this talk is sort of a broad amalgamation of 3 sets of papers, including one that's going to be later at AFT. But I'll stop right now, and I'm already a minute overboard. And if there are any questions, happy to talk about it.
Thank you so much. Any questions? Okay.
A very nice talk. Actually, I'm also very interested in database research. One of the major difference between database transaction and the blockchain transaction is, as you probably know better than I, is a database transaction is most of the time is certain, but in a blockchain it's uncertain. There's also a delay and latency in it, and also some forking. Sometimes the transaction is canceled. So does your research consider some question like this or any existing work like this? Just my question.
So it comes down to the model that we are working with. So as you say, right? So the class of questions that we studied in sort of classic database theory, they don't really sort of address some of these challenges in the blockchain ecosystem. So the closest thing that we've done, at least in the way we are, the so-called the deferred execution model that most clients use, is to sort of transform it to a classic database problem where you say that, okay, I leave it to the proposer to come up with a deterministic ordering in which I just want to execute those blocks. And now my goal is to just execute it in that order. When I say I, meaning the set of validators. Now that model is, as I said, constantly changing because it comes with a significant constraint because you're forcing, the nature of this determinism means that you're forcing everyone to respect this order, and the kind of scalability that you can get from this model is limited by sort of classic lower bounds. So this is changing. So the way this is changing is by introducing, is by moving this problem to preparing the block itself at the mempool level. So, you decide, okay, these are the set of blocks that, go, these are the set of transactions that go in this block because I think the set of transactions in this block are not conflicting too much with each other, or they have very little dependency, or because I want to prioritize for some reason because it belongs to a set of D apps that I think are more important to me, But then that sort of raises fairness questions and MEV questions and all of those other questions that come. So as soon as you go away from determinism, those problems come into play, and then you'll have to look for other solutions for it. Right now, there is, I don't think, any real agreement in the community on which model is the best. My taxonomization is one attempt to at least put a mental picture for everyone for these different models, but I don't think there's like an answer that we can settle on right now. And this is also very dependent on the EVM world is very different from the Move world, simply because the two memory models are very different. Solana is its own different thing. So it's also very specific to EVM versus Move versus Solana, at least speaking. I hope that answers your question, but the short answer is I don't think there's like any well-defined model that people are working with in order to address this.
Thank you.
There is another question.
Hi, nice talk. I'm curious about, so one difference in the classical world is you have a single person who execute and then the result is all set. But on blockchain, you have the proposer and the validators, they have to execute and be able to verify the result is the same. So for parallel computation, how do you encode the information of those computations inside the block so that the others will be able to validate?
Thank you for the question. So with respect to this model of parallel computation, this is identical to the model of computation when it's done sequentially. So, literally, nothing changes, in terms of code for, in terms of what the proposer does and in terms of what the validator does. The validator, just instead of running that code on a single-threaded instance, runs it in a multi-threaded instance, with the guarantee that the output from the multi-threaded instance is going to be the same as the output from that single-threaded instance. So we are not fundamentally changing this model in this setting. As I said, even with respect to the other person's question, this is changing because simply because of the restrictions that come with this model, and there are solutions here, especially in terms of there are a couple of academic works at least talking about distributed transactions in the Byzantine setting, where they would have go through another round of consensus, probably in a smaller clan setting that allows them to sort of agree on the set of orderings that validators would need to execute. But the latency versus throughput gain trade-off, I think, is still something we are yet to understand. And again, as I said, there are probably more benefits in exploring this in the EVM world, simply because I think, especially with ERC20 transactions, there are like more scopes for, quick parallelism solutions. It's probably a little bit harder in the Move world. It's probably more possible in Solana. So Solana, for instance, right, the proposers actually tag the read and write sets when they are sent to the validators. So that's why it's in the read-write-aware model. Now, they assume that this is correct by the time it gets to the validators, and they go through another round of revalidation just to make sure that the state is consistent, which increases the overhead, but that's their solution at this moment.
Okay, thank you.
Okay, maybe one quick question.
Hi, thanks for the talk. How effective do you think parallelization of these transactions will be if, we move towards a future in which most financial interactions on-chain are incredibly composable? And so when you have one token being lent out somewhere else, being composable with another DeFi platform on an L2 or on the L1 mainnet, regardless of what chain you're on, if there's many interactions happening, which is maybe the whole premise of on-chain finance, then how effective is parallelization, and especially if they're accessing the same state?
Perfect. Thank you for the question. So this talk was restricted to a single virtual machine. So what I think you're alluding to are these cross VM transactions potentially.
Well, cross VM and also, maybe just in Ethereum land, let's say, interacting with Base versus Arbitrum, or even on mainnet, just being composable with one another.
So the question of composable transactions in the parallel setting is also, significantly studied in the sort of traditional database and traditional parallel execution community. So a lot of these parallel execution techniques derive their motivation from traditional transactional parallel execution techniques that exist in the Web 2 world. Like, Amazon uses it, Google's Chubby Lock service uses it. All of them sort of use some form of these composable transactional execution techniques. Just that they're not constrained by some of the limitation of sort of the order in which you want to execute the transactions and so on. So there is, almost like sort of a, to trivialize it, a copy-paste way of sort of transforming, existing composable transaction solutions to this world. Again, with the caveat that, the memory model here that we are dealing with is very different from what we've studied in the Web 2 world and so on. So it's not like we don't know how to do it. I mean, and, not just me, like there are others who have been studying composable transactions and how to parallelize them in the classic sense of composability. But I don't think there are like sort of, open source or sort of well-defined, well-studied solutions. But it is something that I'm personally interested in, and I know for a fact there are others looking into it, especially in the Ethereum world.
All right, thank you so much. Let's thank Srivatsan one more time. Thank you.